Assalamu alaikum warahmatullahi wabarakatuh. My name is William Diaz and my topic of presentation is boron nitride nanotubes. My roll number is 2500914005. First of all, we will discuss about the introduction of boron nitride nanotubes. Boron nitride nanotubes are a novel form of one-dimensional nanomaterials with a rolled tube structure composed of alternating boron and nitrogen atoms arranged in a hexagonal lattice similar to carbon nanotubes. However, unlike carbon nanotubes, which can behave as magnetic or semiconducting depending upon structure, boron nitride nanotubes possess a large intrinsic band gap and exhibit consistent electrical insulation across different configurations. Here are some diagrams of boron nitride nanotubes that are represent. There are multi-layered wall 1, wall 2 and wall 3 which are also made up of boron and nitride nanotubes. Then we will discuss chemically. Boron nitride nanotubes are formed from elements of boron and nitrogen whose difference in electronegativity leads to partial ionic and bonding rather than pure covalent networks. Thus we can say that boron nitride nanotubes are chemically made up of boron and nitrogen elements, while the carbon nanotubes are made up of only carbon atoms, and in this they have electronegativity difference in and leads to a partial ionic bonding rather than pure covalent bond networks. This ionic character imparts unique properties including chemical and thermal stability, high mechanical strength, and electrical insulation. Here is the difference between boron nitride nanotubes and carbon nanotubes. It will tell about carbon nanotubes are black and then lower in temperature, 400 degrees Celsius in temperature in air, metallic or semiconducting, while on the other hand boron nitride nanotubes are white, higher temperature. This is because they have ionic character, and boron transfer its electron to the higher electronegative element nitrogen, while in carbon nanotubes there is a polar covalent bond exists. In boron nitride nanotubes, electrical insulator, piezoelectric effect, no absorption in visible spectrum, high neutron absorption, and this is because they have high strength, high stiffness, high thermal conductivity, and high aspect ratio and low density. Then we will discuss about the chemistry and synthesis of boron nitride nanotubes. In terms of chemistry, boron nitride nanotubes originate from hexagonal boron nitride nanotubes precursors, where layered sheets of boron and nitrogen atoms roll into hollow cylindrical nanotubes under high temperature and controlled conditions. Thus, we can see that boron nitride nanotubes are made up of boron precursors, and then can be layered into sheets and rolled up by the sheets of boron and nitrogen atoms into hollow cylindrical nanotubes under high temperatures, and we can also maintain the conditions under which nanotubes are made. The elemental composition and bonding arrangement give them structure, integrity, and chemical resistance capable of resisting oxidation up to temperatures above 800 degrees Celsius temperature. Then boron nitride nanotubes are synthesized using a variety of methods, each grounded in different scientific principles of chemical reactions and physical formation mechanisms. Common methods include arc discharge, chemical vapor deposition, ball milling, followed by high temperature annealing and laser ablation. Arc discharge and CVD walk a fine balance between thermal energy and reactive gas environments to facilitate the growth of boron nitride nanotubes to form from boron and nitrogen sources. In CVD means chemical vapor deposition. For example, a boron containing precursor decomposes at elevated temperature in the presence of nitrogen gas, allowing boron nitrogen bonds to form and curving into nanotubes as they self-assemble. That we can say that we should maintain temperature, and in the gaseous environment the boron precursors are then break down and then they form sheets of boron nitride nanotubes. Then here are some diagrams of boron nitride nanotubes. then we will discuss about Then we will discuss about the forming and tailoring boron nitride nanotubes alloys and composites, as well as everything that we can be synthesized have its own properties. But when we also make alloys, it will enhance its characteristics more and more, and we will attain a better property of materials to enhance its mechanical strength, stiffness, and other properties. Here we will also discuss about the forming and tailoring of boron nitride nanotubes, alloys, and composites. Although boron nitride nanotubes are distinct chemical structures, they can also be alloyed or incorporated into composite materials to achieve tailored properties. Scientifically, alloys or nanocomposites are typically made by uniformly dispersing boron nitride nanotubes within metal or polymer matrices and sintering them under controlled heat and pressure. Metal matrix composites such as boron nitride nanotubes, reinforced aluminum 7075, or titanium alloys are synthesized through methods like cryomilling and spark plasma sintering to generate strong interfacial bonding and defined microstructure. The scientific rationale is that boron nitride nanotubes is due to their high Young's modulus and excellent thermal stability act as nano reinforcements that impede dislocation motion in metals, thereby increasing the overall yield and compressive strength of the composite. This tailoring process allows engineers to optimize mechanical properties such as stiffness, toughness, and high temperature performance attributes critical in aerospace and art structural applications. Then we will discuss tailoring boron nanotubes properties. Once a boron nitride nanotubes alloy or composite alloys or composite is formed, intrinsic properties like thermal conductivity, mechanical reinforcement, and electrical characteristics can also be manipulated through doping or functionalization. Doping refers to introducing foreign atoms or molecules to boron nitride nanotubes to modify their properties, such as making them responsive to fields or changing optical emission behavior. Boron nitride nanotubes can also be functionalized to enhance interfacial interactions with matrix materials or tune their surface chemistry for specific applications. For instance, controlling tube diameter, wall thickness, and alignment strongly affects mechanical strength and thermal support. Increasing alignment within a composite facilitates efficient load transfer and improves directional thermal conductivity, making boron nitride nanotubes composites suitable for high performance structural components. Then we will discuss synthesis method of boron nitride nanotubes. There are several synthesis method of boron nitride nanotubes. The synthesis of high quality boron nitride nanotubes remains a significant scientific and technological challenge. Several methods have been developed, each with specific advantages and limitations. Here we will discuss first of all arc discharge method. The arc discharge technique involves generating a high temperature plasma between boron containing electrodes in nitrogen rich environment. This method can produce boron nitride nanotubes with relatively high crystallinity. However, control over tube diameter, length, and purity is limited. This process also requires extreme conditions and yields low quantities. Here we will discuss about the advantages. The main advantage of this process is that it produces high crystalline boron nitride nanotubes with good structural quality, and boron nitride nanotubes have few defects and good mechanical strength. Here are some also limitations, as all the processes have advantages as well as disadvantages. Here are some limitations. There are some limitations of this process. Also, it requires very high temperature, 3000 to 4000 Kelvin. It gives low yield of boron nitride nanotubes compared to other methods. It contains many impurities such as amorphous boron and catalyst particles. Then we will discuss about laser ablation method. In the laser ablation method, a high powered laser is used to vaporize a boron containing target in the presence of nitrogen gas. This technique allows better control over synthesis conditions and produces high quality boron nitride nanotubes, but it is expensive and not suitable for large scale production. Then we will discuss about the advantages, as all the processes have some advantages as well as some disadvantages. The main advantage of this process is that it produces high purity and well aligned boron nitride nanotubes. It gives excellent crystallinity and uniform structure. Here are some also limitations. It requires high power laser system and it is very costly. It also gives low yield. It gives excellent crystallinity and uniform structure. Then we will discuss about limitations of this method. It requires high power laser system and it is very costly. It also gives low yield and not suitable for large scale production. We can say that it can be applicable to at a laboratory level, but it will not be applicable to industrial level. Here we will also discuss about another method, chemical vapor deposition method. Chemical vapor deposition is one of the most promising methods for boron nitride nanotube synthesis. In this approach, boron nitride containing precursors react with nitrogen or ammonia at elevated temperature in the presence of catalyst. As there will also present catalyst in this system, CVD offers better control over nanotube growth, scalability, and integration with substrate, making it suitable for industrial applications. Advantages, here are also some advantages of this process. It is the most promising method for large scale boron nitride nanotubes production with better control over length, diameter, and morphology. Thus, we can say that this method is applicable for large scale production. And there are also some limitations of this process. Boron nitride nanotubes may contain structural defects in the use of structural defects. This use of catalyst may introduce metal impurities. Thus we can see that here are some methods. These images shows different methods: laser ablation method, chemical vapor deposition method, arc discharge method, as we already discussed above, template, ball milling, and autoclave method for the synthesis of boron nitride nanotubes. Then ball milling and annealing. This method involves mechanical milling of boron powder followed by annealing in a nitrogen or ammonia atmosphere. Although it is relatively simple and cost effective, this method is simple and cost effective. The resulting boron nitride nanotubes often exhibit structural defects and low purity compared to those produced by CVD or laser ablation. Then we will discuss about the advantages of this process. It operates at relatively low temperature and pressure. It is usually with simple and low cost. Here are also some limitations. It produces boron nitride nanotubes with lower crystallinity, and it is mostly useful for laboratory scale. Autoclave method are solvothermal technique where boron precursors react with nitrogen sources in a sealed autoclave at high temperature and pressure, leading to the formation of boron nitride nanotubes with controlled morphology but relatively low yield. It is also a technique that is used for the production of boron nitride nanotubes. As we already discussed the advantages and limitations, we will also discuss about the advantages and limitations of this process also. What are the main advantages of this process? The main advantage of this process is that it requires low synthesis temperature compared to arc and laser ablation method. It is usually simple and inexpensive technique equipment. Here are also some limitations. It produces boron nitride nanotubes with lower crystallinity, that we cannot get boron nitride nanotubes with higher crystallinity in this process. It is also not suitable for large optical or industrial production. In this process it may also contain impurities or mixed boron nitride nanotubes phases. As we will discuss all the processes for the formation of boron nitride nanotubes, their advantages as well as limitations. Now we will discuss about boron nitride nanotubes in semiconductor technology and dielectric use. From a semiconductor perspective, boron nitride nanotubes are fundamentally different from traditional semiconductor materials like silicon or gallium arsenide. Because boron nitride nanotubes have a wide electronic band gap, they behave as electrical insulators rather than conventional semiconductors. However, this electrical insulation combined with high thermal conductivity and excellent dielectric properties makes boron nitride nanotubes extremely attractive as dielectric materials or insulating layers in electronic devices. Boron nitride nanotubes filled into packaging materials or thin films can reduce parasitic capacitance and improve device performance at high frequencies. Dielectric constant values measured in boron nitride nanotubes mass show extremely low dielectric constant, key for microelectric packaging where reducing capacitance and power dissipation is crucial. This makes boron nitride nanotubes candidates for next generation interlayer dielectrics in ultra large scale integration circuits. Although boron nitride nanotubes are not used as active semiconductor channels like doped silicon or gallium nitride, they serve supporting roles, for example, as thermal management structures in semiconductor chips or protective insulating coatings for nanowires and field emitters. Then we will discuss about the advantages and limitations of boron nitride nanotubes in semiconductors. In comparison to traditional semiconductor materials, boron nitride nanotubes provide distinguishing advantages such as superior thermal stability, high thermal conductivity, high electrical breakdown strength. They also display radiation hardness, which make them suitable for space electronics and radiation tolerant systems. However, because they are wide bandgap insulators, they cannot replace materials like silicon in active transistor channels, but rather complement them as thermal or dielectric materials. Thus, while they are not inherently better than silicon for active semiconductor behavior, boron nitride nanotubes excel where heat dissipation and electrical insulation are paramount, enabling improved performance and reliability in high temperature and higher power electronic applications. Broader applications beyond semiconductor use. Beyond semiconductor technology, boron nitride nanotubes have a wide range of applications due to their mechanical strength, thermal stability, low density, chemical inertness, and biocompatibility. These include aerospace components, radiation shielding materials, composites for automotive or sports industries, biomedical nanocarriers, and sensors. Their neutron absorption capability from boron isotopes enables shielding applications in nuclear environments, and their piezoelectricity allows use in mechanical sensors or energy harvesters. Conclusion क्या है? Then we will discuss about the conclusion of this topic. In summary, boron nitride nanotubes represent an exciting and distinct class of nanomaterials. Their high mechanical strength, thermal robustness, insulating nature, and tunable properties make them valuable for advanced composites, dielectrics, and components in high temperature and high frequency systems. While not replacing silicon as semiconductor, their role is in supporting semiconductor performance and reliability is significant. Boron nitride nanotubes research is rapidly advancing a new synthesis and alloying methods improve yield and quality for broader industrial deployment. Here are some references from which source it is taken, and this is all about my topic about of boron nitride nanotubes. Thus, we can say that boron nitride nanotubes are those that have high mechanical strength, stiffness, and they are semiconductor and can be used in no advanced technological instruments, and because of their high strength and stiffness. This is all about boron nitride nanotubes. Thank you so much.